talk a little bit more about kinematics and derive some important new formulas. So, kinematics, call this kinematics 2. So we're going to do a little recall. This is stuff that you already know. You know this. Velocity is a change in displacement over a change in time. And we also learned this. When you have a changing velocity in a time period, you have an acceleration. These are vector values, okay? And these can help you solve fairly simple and straightforward kinematics problems. Okay, so something else to remember from your past learning is, let's say that we have a velocity time graph, okay? So what this is laying down for you is what is happening with the velocity as time goes by, okay? So let's imagine we have an object traveling along on a number line, okay, like this, at a constant velocity, okay? So here's a number line. That means if we take a picture of them at, the same interval, what we'll find is that they're just moving along constantly. Okay, are you with me? So if we were to graph that on a velocity time graph, we should expect to see that the velocity does not change. Okay? The velocity does not change during the time. Okay? And if you look at this formula, you'd see that you can rearrange it, right? You can rearrange it to solve for delta D. You could say the change in displacement should be equal to the velocity that we have for the time period that we're talking about. This makes sense, right? If I drive 100 kilometers per hour for 4 hours, it would make sense to you that you've gone 400 kilometers, right? 100 times 4 hours cancel out. Oops, I should not have put a negative there, but 100 times 4, 100 kilometers per hour times 4 hours works out to be 400 kilometers, okay? Now let's look at that. What we actually did was we said we took the velocity that we were dealing with and we multiplied it by time, okay? What did that tell you from this graph? Well, what it tells you is it tells you the area underneath this graph, right? So this area under here, the area under the velocity time graph, I don't know if you remember this from last year or not, but if you don't, this is your refresher. The area under this graph gives you the displacement, okay? So let's just, let's write that down. Okay? Because it's kind of important. So we'll say the area under a velocity time graph equals displacement. And how you find that is, well, you find the area under this graph. In this case, the displacement that you went, delta D, the change in displacement, is equal to the velocity you traveled at times the time, aka the area under this graph. Does that make sense to you guys? Okay, this is about as far as you got with last year. But what happens if this is going on? Okay, what if you get asked this question? The car is initially at 0 meters per second, and it accelerates to 20 meters per second over a 5-second interval. Find the distance it covered while speeding up. Can you do that? Okay, let's see how we're gonna deal with this. So, first thing I want to do is I want to graph what this is gonna look like. Okay. All right. So here's our velocity, and here's our time. okay? And what I think you'll see is that the velocity is now increasing. You have an accelerated velocity, so you've got this thing going on here, right? Okay. So let's think a little bit about what we're dealing with here, okay? So we're going to put in some little guidelines to help us think about this problem. I'll put that in there, okay? And I'm going to put this in here, okay? And let's fill in some values. So this is VF right here, right? And VF was 20 meters per second, okay? And that happened over a 5-second interval. So there's 0 seconds. And VI equals 0. Now what we're looking for, right? Really what we're looking for is the area bounded by this, because we just reviewed that the area under a velocity time graph should be equal to displacement. Okay? But how we're going to find this is a little bit maybe different than you might expect, okay? So this is what we're going to do. We're going to say if we were to go exactly halfway up this thing, okay, so here, that's not a straight line. I want a straight line. I'm going to get a straight line. Let me get a straight line. Okay. What you'll notice here, okay guys, what you'll notice here is that there's kind of two areas here, and I'm just going to bound them off. Uh-oh, that didn't work. I'm just going to bound them off, okay? So there's this area that is under your triangle, right? All of this. Yeah. Okay. And then there's a rectangle. And what you'll find is that this area of the triangle can actually like fold over and exactly fit in there. Okay, so we can put that in there. So in other words, what I'm saying to you is that this rectangle that we bounded off here, will have the exact same area as the triangle that we drew up here. Okay? Why is that true? Well, look, here's a large square, right? This line deviates exactly half of this square, right? Half below, half above. But there's another way to split a square into two halves, right? Cut it in half this way, and this area will be the same. So in other words, the area under the triangle and the area in the rectangle are identical. Okay? So this leads into us being able to solve a new formula here. Okay? So if we want to find, oh, I don't want that to be like that anymore. I want it to be like this. Okay? We have VF, we have VI. How do we find the average between the two? Well, you go VF plus VI, and you divide it by 2, right? VF plus VI divided by 2 will give you this line right here. Regardless of what VI and VF happen to be in terms of numbers, you will get that value. And so it's just one more like mental step to see that if we have VF plus VI over 2 being this line, all we'd have to do is multiply it by time to find how far that thing went while it was accelerating. So this is a brand new formula for you to have and use to deal with finding displacements during the acceleration of an object. Okay? You have to be careful though. This formula does not solve the same problems that this formula does. Okay? This one is for something with a constant velocity. This one is for one with a changing velocity. Do you see that? Don't mix up when you use them, okay? So let's put a little bracket around here. You'll find this on your formula sheet, okay? And there's one more thing I'm going to show you here. Okay, and just one more thing that I want to deal with here. You have this formula, right? From last year, if it lets me draw it. you have this, right? You with me? Delta V is the same as saying final velocity minus initial velocity, t. Okay? Or we could say this. If we rearrange this, right, multiply by t, bring the t over here, vf minus vi equals acceleration times time. And the one last thing that we do is we could say the final velocity should be equal to the initial velocity plus acceleration times time. This is just taking that formula and expanding it. Okay, and this is actually a delta t. It's the time span we're talking about. I'm not super concerned about you having that delta in there. But finding a final velocity when you have an initial velocity, right? And you have an acceleration, and you have a time. So if we just skip back to this one, okay? Let's actually solve this and figure out what value we would get for it, okay? So what you should get is you should get d equals, well, vf plus vi, well, vf is 20 meters per second plus 0 divided by 2 times 5 seconds. So you should get 10 times 5, or you should get 50 meters. So in other words, half as far as he would have got if he had gone at his final velocity the whole time. Okay, and then just for a last little thing, let's solve something with this. A car is at 5 meters per second and accelerates at negative 0.5 meters per second for 5 seconds. Find its final velocity. So let's just talk about what's going on in this picture. I'll let you guys write this down, and then we'll draw a picture of this. Okay, and sorry, just to clarify here, this is its final velocity. Final velocity. So when we say a negative acceleration, but I guess what we mean, well, you got to be careful, because it's not necessarily that it's slowing down, okay? That's not something you can say for sure, because negative accelerations can cause things to speed up. So look, remember that with vectors, positive and negative really mean left and right, okay? Right, so people oftentimes do have trouble understanding what we mean in a scenario like this. So this is the way I try to help them. Remember that Newton's second law says F equals ma. Examine what that means. Essentially what it means is, if you want to accelerate something, you have to push it or pull it, right? So if velocity is positive and acceleration is negative, all that really means, you can think of it like something is pushing on it to the left. So will this car speed up or slow down in this scenario? It'll slow down, right? If it's traveling to the right and you're pushing to the left on it, it's going to slow down. But here's another good question, just before we actually solve it. What if the car were traveling to the left already, and we applied a negative acceleration to it? Then what would happen? Correct. So then, in that case, if it already has a negative velocity, and we apply a push on it to make it accelerate, this is a negative acceleration, and it's causing something to speed up. So you have to be a little bit careful. Here's a good thing to remember, okay? Look, velocity, right? And acceleration, okay? Or, hang on, not done yet. Or, yeah, I don't know why it does that. Or this. These are the only really scenarios that you could possibly have, okay? Take a look. If velocity is right and acceleration is left, an object will slow down. It's as if we're pushing against it to the left, right? If an object's traveling left and we're pushing to the right, that's also going to make it slow down. So this is negative velocity, positive acceleration. That causes slowing down. We could have positive velocity and positive acceleration. That would cause speeding up. And we could have negative velocity and negative acceleration, and that could cause slowing down. So in this case, we have positive velocity, negative acceleration, car slows down. It doesn't slow down because of the word negative. It slows down because of the way that velocity and acceleration are interacting with each other. Okay, so let's just go ahead and solve here. All right, so we just want to find our final velocity. And we've got VI of 5 meters per second. So it's traveling at 5 meters per second. And we're going to add to that our acceleration, which is negative 0.5 meters per second squared. Sorry, this should be squared. My bad. And multiply it by 5 seconds. And what do we get? What do you get? This is a negative value, right? Exactly. 2.5 meters per second. So the car has slowed down. It is not negative 2.5.